Welcome back to AI.Code.Cast, everyone. Today, we're going to dive into a problem that's a favorite in coding interviews. It's the odd-even linked list rearrangement.
Yeah.
Yeah, it's one of those challenges that can really make you think, and helps demonstrate a solid understanding of linked lists.
It really does. It's a great way to see if someone can think beyond just the basic operations and really get creative with how they manipulate data structures.
Right, so before we get into the solutions,
Yeah.
let's set the stage for our listeners.
Yeah.
Imagine we have a singly linked list, the kind where each element points to the next one in line.
Right.
Our goal is to rearrange this list so that all the odd index nodes come before the even index ones.
Yeah, and it's not about sorting the values themselves.
Right.
We're focused on the positions. It's like we're separating the list into two teams, odds and evens, and then having the odds line up first.
Okay, that's a great analogy. So if we had a list like 1, 2, 3, 4, 5,
Right.
we'd want to end up with 1, 3, 5, 2, 4. The order within the odd and even groups stays the same. We're just kind of like interleaving them.
Exactly. Now here's where the real challenge comes in.
Okay.
We need to do this with O1 space complexity.
Okay.
That means we can't create any new data structures that grow with the size of the input lists.
Right.
We have to work within the confines of the original list itself.
Ooh, that's a tight constraint. It feels like trying to solve a puzzle in a tiny box.
It definitely forces you to be resourceful.
Yeah.
So with that constraint in mind, where do you think we should start?
Well, the first thing that pops into my head is, what if we just create two new lists as we go through the original one for odds and one for evens, that we can just link those two lists together at the end?
That's a very natural instinct, and honestly, it's a valid approach to solving many problems.
Yeah.
However, in this case, creating those two new lists would require ON space, where n is the number of nodes.
Okay.
We'd essentially be duplicating the data, and that breaks our space constraint.
Oh, right. That's a classic pitfall.
Yeah.
So creating separate lists is a no-go.
Yeah.
It seems like we need a way to rearrange things within the original list itself.
Precisely. We need to get clever with how we manipulate the pointers, those connections between the nodes.
Pointers.
Yeah.
I'm starting to think about how we could potentially swap nodes around, like maybe detaching and reattaching them in a different order.
You're on the right track.
Okay.
Remember, we want to separate the odds and evens while maintaining their relative order.
Right.
Think about how you could do that by strategically changing what each node points to.
Okay, let me visualize this.
Yeah.
What if we start with two pointers, one at the beginning of the list and one at the second node? Maybe we could call them the odd pointer and the even pointer.
I like where you're going with this.
Okay.
Now, how would you move those pointers to start separating the odd and even nodes?
Let's see. If we have the odd pointer at node 1, maybe we could make it skip over node 2 and point directly to node 3. That would effectively detach node 2 from the odd sequence.
Excellent. You're essentially weaving the list.
Okay.
Now, what would you do with the even pointer, which is currently at node 2?
Well, if the odd pointer is now at node 3, maybe we can make the even pointer skip over node 3 and connect to node 4.
Okay.
That way, we're building up separate chains for the odds and evens.
That's exactly right.
Okay.
We're essentially untangling a braid, separating the strands, and then reconnecting them in a new order.
This is starting to feel like a dance, where the pointers are gracefully moving around, partnering up with different nodes.
It's a beautiful dance of efficiency.
Yeah.
We're manipulating the pointers to achieve our goal without using any extra space.
Right.
But we're not quite done yet. What happens when we reach the end of the list?
Good point.
Yeah.
We'll have two separate sublists.
Right.
One with all the odds and one with all the evens.
Yep.
How do we join them together to form the final rearranged list?
That's the final step in our choreography.
Okay.
Think about how you can connect the tail of the odd sublist to the head of the even sublist.
Okay, so if we have a pointer tracking the last node of the odd sublist, we can simply make it point to the first node of the even sublist.
Yes.
That would effectively merge the two chains.
You've got it. And with that, our linked list is rearranged according to our odd-even criteria, all done in place.
That is so cool. By carefully orchestrating these pointer movements, we've achieved our goal efficiently and elegantly.
It is pretty neat.
But you mentioned there were other ways to solve this, right?
There are.
Okay.
Sometimes a different approach can lead to code that's easier to understand and maintain, even if it might not be as algorithmically clever.
I'm all ears. Let's explore these other approaches in part 2 of our deep dive. All right, we're back, and I'm still buzzing about that pointer weaving technique.
Yeah.
It's amazing how much you can accomplish just by, cleverly rearranging connections.
It really is. It's a testament to the power of thinking about data structures, not just as static containers, but as dynamic networks where relationships can be shifted and reformed.
Yeah, I love that perspective. But you mentioned there are other ways to solve this odd-even linked list problem.
Right.
What's another approach we could take?
Let's talk about a technique that might seem a bit counterintuitive at first, but can actually make the code much easier to follow using dummy nodes.
Dumb units. Okay, that sounds intriguing and maybe a little mischievous.
Yeah.
What are they, and how do they help us with this problem?
So think of a dummy node as a placeholder.
Oh,
A temporary stand-in. It doesn't hold any real data from our original list,
right.
but it acts like an anchor, a starting point for building up our rearranged sublists.
So instead of trying to figure out where to attach the first odd or even node directly, we use these dummy nodes as convenient starting points.
Exactly. Imagine we create two dummy nodes, one for our odd sublist and one for our even sublist.
Okay.
We'll also have two additional pointers,
Okay.
one pointing to the end of the odd sublist and one pointing to the end of the even sublist.
Okay, I'm picturing these two dummy nodes, like the heads of two separate Congo lines, each waiting for dancers to join in.
Perfect analogy. Now, as we iterate through our original linked list, we look at each node's index.
Right.
If it's odd, we attach it to the end of the odd conga line by updating the odd tail pointer.
Okay.
If it's even, we do the same for the even conga line.
So it's like we're sorting the dancers into their respective conga lines as they come along, using our tail pointers to keep track of where each line ends.
You got it. And by the time we've gone through the entire original list, we have two neatly formed conga lines, one for odds and one for evens.
And then the final step is simply to connect the end of the odd conga line to the beginning of the even conga line, right?
Precisely. Just like that, we've merged our two sublists, creating a final rearranged list that fulfills our odd-even criteria.
Yeah, I see the appeal of this dummy node approach.
Yeah,
It feels more organized, like we're deliberately building our sublists step by step instead of doing all the weaving and swapping in place.
it often leads to code that's easier to read and less prone to errors, especially if you're new to linked list manipulations.
Right.
And in the grand scheme of things, the extra step of creating those dummy nodes doesn't significantly impact our time or space complexity.
It's still an O1 space solution because those dummy nodes are just constant overhead.
Right.
And I can see how having those clear starting points simplifies the logic. Sometimes a bit of extra setup can make the overall process smoother.
Absolutely. Now, both the weaving technique and the dummy node approach are valid ways to solve this problem, and each has its own strengths.
It's like choosing between a nimble sports car and a reliable SUV. Both can get you to your destination, but the choice depends on your preference and the terrain.
Exactly. Sometimes elegance and conciseness are prioritized, while other times clarity and maintainability are key.
Yeah.
It's about understanding the trade-offs and choosing the right tool for the job.
Okay, so we've got two solid iterative solutions under our belt. But I'm curious, could we tackle this problem using recursion? I know it's not always the most efficient way, but sometimes thinking recursively can unlock a different understanding of the problem.
That's an insightful question, and you're right, recursion can offer a unique perspective.
Yeah.
While it might not be the most practical choice for this particular problem, it's worth exploring how a conceptual recursive solution would work.
Let's dive into that. I'm ready to get a recursive.
All right, so the heart of any recursive solution lies in breaking down the problem into smaller, self-similar subproblems.
Right.
In this case, we need to figure out how to rearrange a linked list as odd-even, assuming that we already know how to rearrange a smaller linked list in the same way.
So it's like saying, if I can solve this problem for a shorter list, can I use that solution to solve it for a longer list?
Precisely. And that's where the concept of a base case comes in.
Yeah.
It's the simplest version of the problem that we can solve directly without any further recursion.
Right.
For this scenario, what do you think the base case would be?
Well, if the list is empty or only has one node,
Yeah.
it's already sorted in terms of odd and even indices, right? There's
Yeah.
nothing to rearrange.
Exactly. That's our base case.
Okay.
Now, for the recursive step, imagine we have a list with more than one node.
Okay.
What we'll do is recursively call our function on the sublist that starts from the third node, effectively skipping over the second node.
So we're essentially saying, go rearrange the rest of the list, starting from the third node, and assume you already know how to do that.
You've got it. When that recursive call returns, we'll have a rearranged sublist where all the odd indices from that point onward are in the correct order.
Okay.
The second node, which is even, will still be hanging out in its original position.
Okay, I see where we're going with this.
Okay.
So now we have this correctly ordered odd sublist, and we just need to figure out how to insert the second node and any other even nodes that were skipped back into the list in the right place.
Exactly. And this is where we'll leverage pointer manipulation again. We need to carefully detach the second node and reattach it at the end of the rearranged odd sublist.
So we'd make the first node point to the third node,
Yep.
effectively detaching the second node,
Ta.
and then find the end of the odd sublist and make that last node point to the second node.
You're spot on. Now we've successfully placed the second node, which was originally in an even position, at the end of the odd sublist.
Okay.
And we can repeat this process for any other even nodes that were skipped over during the recursive calls.
So it's like we're strategically plucking out the even nodes and stitching them back into the list at the end of the odd sequence.
Precisely. And with that, we've recursively rearranged our linked list according to our odd-even criteria.
This recursive approach is conceptually interesting, but I have a feeling it might not be as efficient as our iterative solutions, right?
You're right to be cautious.
Yeah.
Recursion often comes with a cost in terms of space complexity, especially when dealing with data structures like linked lists.
Because each recursive call adds a new frame to the call stack. And if our list is really long, that stack can grow quite large.
Right. That's exactly the trade-off we're making here.
Yeah.
The recursive solution, while conceptually elegant, might not be the most practical choice when we have a strict space constraint.
Right, it's like choosing to take a scenic route instead of the highway.
Yeah.
It might offer a different perspective, but it could take a bit longer and require more resources.
That's a great way to put it.
Yeah.
So while understanding the recursive approach can broaden our understanding of the problem,
Right.
for real-world scenarios where efficiency is paramount, our iterative solutions with O1 space complexity are the way to go.
Okay, so we've covered 3 distinct approaches to the odd-even linked list rearrangement. 2 efficient in-place solutions, and a conceptual recursive solution that sheds light on the problem's structure.
Right.
What are your final thoughts for our listeners as we wrap up this deep dive?
Yeah, it's been a fascinating journey exploring this seemingly simple problem
It has.
and discovering the depth of thought it requires.
Right. We've talked about pointer manipulation, dummy nodes, recursion. It feels like we've leveled up our linked list skills today.
Absolutely. This problem really highlights how important it is to consider not only the correctness of a solution, but also its efficiency and clarity.
Right. It's not just about getting the job done. It's about doing it in a way that's both elegant and maintainable.
Exactly.
So for our listeners who are maybe feeling a bit overwhelmed by all these approaches, let's do a quick recap of what we've learned.
Okay, so let's rewind.
Yeah.
We started by considering a brute force approach, using separate lists for odds and evens, but quickly realized it violated our space constraint.
Right.
It was a good lesson in identifying potential pitfalls early on.
Then we dove into the world of in-place manipulation,
Yeah.
exploring 2 clever solutions that achieved O1 space complexity.
Right.
The weaving technique was all about carefully swapping pointers to interleave the odds and evens.
It's like a carefully choreographed dance where each node takes its turn in the spotlight.
And then we had the dummy node approach, which felt a bit more structured.
Right.
It's like we built 2 separate conga lines and then merged them at the end.
That approach often leads to code that's easier to follow, especially for those who are newer to linked list manipulations.
Yeah.
Sometimes a bit of extra setup can actually simplify the overall logic.
Exactly. And finally, we took a detour into the land of recursion.
Right.
While it wasn't the most efficient solution in this case, it offered a different perspective on how to break down the problem into smaller, self-similar steps.
Recursion can be a powerful tool for problem solving, but it's important to understand the trade-offs in terms of space complexity and potential overhead.
Now, I have a challenge for all our listeners out there.
Okay.
Think about what we've learned today and consider how you would implement these solutions in your favorite programming language.
Seeing the code in action can really solidify your understanding and help you develop a deeper intuition for how linked lists work.
And here's a bonus challenge. What if instead of separating odds and evens, we wanted to rearrange the list based on some other criteria? Maybe separate nodes based on whether their values are positive or negative.
That's a great way to take what we've learned today and apply it to a new problem.
Yeah.
It encourages you to think about the underlying principles of linked list manipulation and how they can be adapted to different scenarios.
Exactly. It's all about building up that problem-solving toolkit and feeling confident in tackling whatever coding challenges come your way.
Well said. Keep experimenting, keep learning, and keep those algorithmic minds sharp.
That's a wrap for today's deep dive on AI.Code.Cast. We hope you found it insightful and inspiring.
Yeah, thanks for listening.
Until next time, happy coding.